This is video 4.1, Vectors. Example 1. Polly walks 1 mile north, 3 miles east, and then 5 miles south. What is Polly's displacement? If we draw out the path that Polly walked, the question is asking for her net displacement. So that is, how far away is her final position from her initial position? So we'll be looking for this vector. Now, we know that she's walked 3 miles to the east, but she's walked a net of 4 miles to the south because she went 1 mile up and then 5 miles back down. So we can simplify the problem, and we know that she's only gone 4 miles to the south total. That creates a nice right triangle that's easy to work with. We're trying to solve for this displacement vector, and to know the vector is to know its magnitude or length and its direction. So we'll also need to solve for this angle theta. Students often ask me, well, which angle in the triangle do I solve for? To answer that question, you should always solve for the angle that is at the beginning of the resultant vector. So this is the vector we're trying to solve for, and the beginning of the vector is back here, not by the arrow, but back here at the beginning. That means this is the angle I'm trying to solve for. Okay, let's start with the magnitude, or the length of that hypotenuse. So for that we can use Pythagorean's theorem, plug in our side lengths, and solve for the displacement. And you get 5 miles total. Now we need to know this angle theta. So for that we'll use tangent, since the values we know are the opposite and adjacent sides to that angle theta. So tangent theta equals the opposite side of 4 over the adjacent side of 3. Taking the inverse tangent of both sides and plugging this into our calculator, we get 53 degrees. Now that's 53 degrees south of east, or another way, if you're looking at the counterclockwise convention, starting from east, rotating counterclockwise until you hit this displacement vector, we've traveled 360 degrees minus those 53 degrees. And so that gives us a total of 307 degrees. So our final answer is 5 miles, 307 degrees. Let's take quiz number 1. Example 2. An airplane flying at 300 miles per hour due north encounters a 40 mile per hour crosswind blowing due east. What is the airplane's new speed and heading? So the airplane in still air can fly at 300 miles per hour straight north, but then if there's suddenly a crosswind blowing at 40 miles per hour straight to the east, that's going to tend to blow the airplane off course, and it's going to slightly affect the airplane's speed. The resultant velocity will be along this path here. So to know what the airplane's new velocity is, we're going to need to know the length of the hypotenuse and the new angle. Okay, so this is much like the last problem. We can just go ahead and use Pythagorean's theorem to solve for the velocity, plugging in our two side lengths of 40 and 300, and solving for velocity we get 303 miles per hour. Now we can solve for the angle theta using tangent. Tangent theta equals the opposite side of 40 over the adjacent side of 300. Taking the inverse sine of both sides gives us an angle of 7.6 degrees. Now using the convention counterclockwise from east, we're going to have to measure how far away that vector is from the east line. So you can see that to do that we would take 90 and subtract that 7.6 degrees. So that gives us a final answer of 303 miles per hour, 82.4 degrees. Let's take quiz number 2. Example 3. When a boat tries to cross a river, it'll be carried off course by the current in the river. This will give the boat a new velocity and heading. This is pretty much just like the airplane and wind problem we finished previously. Okay, if a boat crosses a river and has a velocity of 15 meters per second and is turned 30 degrees downstream, what is the speed of the current in the river, and what would the speed of the boat be if it were in still water? So this speed that's given, 15 meters per second, is the speed that the boat is traveling as a result of its attempt to travel straight across the stream, and the combined effect of the current in the stream adding to the boat's velocity. So the stream, let's say, is flowing straight down. The rate that the velocity that the river's flowing at, I do not know that value, so I'm going to label it v river. The boat is attempting to cross directly across the river. We'll call that the velocity that the boat could have, let's say, if it were in still water. And the result of those two velocity vectors getting added together will tend to carry the boat a little bit off course. This is the velocity we've been given of 15 meters per second at a 30-degree downstream angle. So in this problem, we know the value of the hypotenuse, and in this case we're looking for the value of each of the sides, the x component and the y component. For this we can use sine and cosine. So starting with sine, the sine of that 30-degree angle will be the opposite side over the hypotenuse, or the velocity of the river over 15. Solving for v river, you get v river equals 15 sine 30, which is 7.5. So the velocity of the current in the river is 7.5 meters per second. Using cosine 30 then, we have cosine is adjacent over hypotenuse. So you have the adjacent side, velocity of the boat, over the hypotenuse of 15. Solving for the velocity of the boat, it's 15 cosine 30, which gives a velocity of the boat of 13 meters per second. Let's look at example 4. I'm going to show you how to do problems where we do not have right triangles 2 different ways. So we're going to do example 4 twice using 2 different methods. So we'll call this example 4a. Alex is running along a path. The path takes him 8 miles north, then turns 30 degrees to the east and continues for another 5 miles. What is Alex's displacement if he runs this path? So we have 8 miles direct, and then we turn 30 degrees towards the east and go another 5 miles. So if you follow that path, your displacement will be the vector that's traced out by this line, what you might call the hypotenuse or the long side of the triangle. This is obviously not a right triangle, and when you're working with triangles that are not right triangles, you cannot use Pythagorean's theorem, nor can you use sine, cosine, and tangent. Those ratios only work for right triangles. So we're going to have to come up with a different method to solve this problem. So one method says, hey, let's take that displacement vector and let's just make it a right triangle. To make this displacement vector, the one I have highlighted in red, how far up and then how far over do I need to go? So I can solve for these values of x and y, or taking this one vector that's off at a funny angle, the 5-mile vector at the 30-degree angle, and breaking it into its horizontal and vertical components. This is a lot like the last problem we just did. So sine 30 equals x over 5. Therefore, the x component is 2.5 miles. Cosine 30 equals y over 5. Therefore, the y component is 4.3 miles. Now we know that it's 4.3 extra miles north and 2.5 miles to the east. So what we can do is add together the 8 miles north with the 4.3 more miles north and say, hey, this problem is the same thing as going 12.3 miles north and then 2.5 miles to the east. Now it's a right triangle. Now I can solve this problem the same way I did any other problem. So I can use Pythagorean's theorem to solve for the displacement. Plugging in our 2 side lengths and solving for d, we get 12.6 miles. And I can use tangent to solve for the angle. Tangent is opposite over adjacent, or 2.5 over 12.3. Therefore, theta is equal to 11 degrees. Now that's 11 degrees to the east of being directly north, or using the counterclockwise convention, that's 90 minus 11 from east. So our final answer is 12.6 miles, 79 degrees. Okay, so that's one way to attack this problem. Let's move on to example 4b, and I'll show you the other way you could attack this problem. So going back to the beginning, I've drawn out the path, and I'm looking for this long side length. I've called it c in this case. Since I can't use Pythagorean's theorem because it's not a right triangle, I have to revert to a different equation. This equation that you see here on the screen is known as the law of cosines. And the law of cosines is sort of similar to Pythagorean's theorem, but the law of cosines works for any triangle. Right triangle, acute triangles, obtuse triangles, any kind of triangle. So let's go ahead and plug into this equation. Now, the side lengths of the triangle we're going to call A, B, and C. And the angles in the triangle, well, we're going to call capital A, capital B, and capital C. So if this is side length C here, then the angle that is opposite over here is angle C. If this is side A, the 5 miles, then this angle over here would be angle A. And if the 8 miles we'll call side B, then this angle would be angle B. The beauty of the law of cosines is that you can, as long as you're consistent, you can call any side you want, A, B, or C. So you could use law of cosines to solve for any side. Okay, so let's go ahead and call this angle C. And do you know the value of angle C? Well, a straight line path, straight line from here straight up would be 180 degrees. So angle C is 180 degrees minus 30, or 150 degrees. So plugging into this equation, we plug in, I'm trying to solve for C, so I'll leave that blank, equals A, we're going to call the 5 miles side length A, so A squared plus B squared minus 2 times A times B times the cosine of angle C, which we just realized or just calculated is 150 degrees. It looks long, but this equation could just be plugged right into your calculator. Plug it into your calculator, one fell swoop. Sorry, I didn't mean to have that repeated there. Take the square root and you get 12.6 miles, the same answer we got when we did the problem the other way. Okay, so that's just the length of side length C, but we also need to know the angle, or angle A. So again, we can use another equation that's set up for any triangle. This is what we call the law of sines, and the law of sines works for any triangle, right triangles included. If the law of sines, you take side length A and divide it by the sine of angle A, and that ratio is the same as side length B divided by the sine of angle B, or side length C divided by the sine of angle C. I'm using this equation to solve for angle A. So if I go back to my triangle here and label my angles, angle A is opposite side A, which is 5 miles. Angle B is opposite side B, which is the 8 mile side. What I want to know is angle A, so I'm going to definitely be using this piece of the equation. But what I know is side length C and angle C. So I need to know these values. So I'm going to simplify this equation slightly and take out the middle portion, B over sine B, because that doesn't help me arrive at my answer. And I can plug into this equation values then that I already have. So side length A is 5 divided by the sine of angle A, that's what I'm trying to solve for, equals side length C, which we just solved for is 12.6, over the sine of angle C, which is 150 degrees. Cross multiply and divide. To solve for sine A, take the inverse sine of both sides to solve for angle A, and you get that angle A is equal to 11 degrees, the same answer we got in the last problem. Now if you take this angle out to a couple more decimal places, you'll see that it might be ever so slightly different than in the last problem, and that's probably due to rounding errors where we rounded off our numbers. Okay, so our final answer, again, measuring counterclockwise from east, excuse me, is 90 degrees minus 11 degrees, or that gives us a total displacement then of 12.6 miles, 79 degrees. Let's take quiz number 3. So when you're solving the problems that use non-right triangles, you can use either method.